Good afternoon, everybody. Thank you so much for having me. My name is Rune. I'm a PhD candidate at the University of Stavanger. My main supervisor is Kjersti Engan, and my co-supervisors are Trygve Eftestøl and Emil Jansen. Today, I'm here to talk to you about my research on automatic grading of bladder cancer using deep learning. Let's start by looking at an overview of the proposed system. This is the pipeline of our proposed system, and I would just like to start with showing you this now, and then I will go into detail of each element afterwards. First, we start with a tissue image from a bladder cancer patient as input. Then we use a tissue segmentation system we have proposed to find all the tissue in the image. Next, we will use a system to extract tiles from multiple levels in the image from the diagnostically relevant areas. Finally, we have a diagnostic model which will predict the grade of the extracted tiles. The output consists of a grade heat map and also a slide level grade. With that brief overview of the flow of the system, let's go into some more details. And we will start with bladder cancer and the input images. Bladder cancer is cancer of the urinary bladder, and as we can see from the figure, has had a significant increase in both incidence and mortalities over the past decades. For patients diagnosed with bladder cancer, we see that 50 to 70% of the patient will experience recurrence, meaning that after the cancer tumor is removed from the bladder, the cancer will come back. And in 10 to 30% of the patient, the cancer will progress to a higher stage. Bladder cancer is also known as one of the cancers with the highest lifetime treatment cost per patient. This shows the importance of correct treatment and follow-up of these patients. Once a patient is diagnosed with bladder cancer, the tumor will be removed. The removed tissue will then be prepared on a glass slide and examined by a pathologist. The pathologist will study the tumor either using a microscope or on a computer with digital pathology. And he or she wants to find the cancer grade, the cancer stage, and also other relevant diagnostic information. These findings will then be used to stratify the patients into risk groups and to come up with a treatment and follow-up plan for the patient. However, the examination is performed manually by the pathologist. It is a time-consuming and challenging job. It is subjective to the pathologist and also have low reproducibility. Therefore, a computer-aided solution is wanted, which would be both objective and reproducible. Here we have an example whole slide image from bladder cancer. It is a digital microscope slide, so the resolution is very high. And when an image size surpasses 1 billion pixels, it is referred to as a gigapixel image. From this image, we can note a few things. First of all, the images can be quite messy. We can see in the top right corner that we have some blood. There are also some blood in the middle of the image. We also have some damaged tissue, which we cannot use for diagnostic. So we need a system to remove these unwanted tissue types from the image. I also mentioned the large size of these images. This specific image is 130,000 pixels times 90,000 pixels, which also provides some challenges. We can't feed the entire image into a deep learning system, but we must extract smaller tiles. And also, we can't use any of the common image libraries when working with these images in Python. Because of the large size of the whole slide images, they are stored in a multilevel file format, in the same way as, for instance, Google Maps uses. This allows for a more rapid zooming in and out of the images. Each level will reveal different information. For example, a histological image will reveal specific diagnostic information at different resolutions, and a pathologist will integrate information across several magnification levels before reaching a decision. I won't go into too much details about what information is revealed at each level, but in general, for the highest magnification scale, it will show the highest level of details about that area. As you go down in magnification, you will get a broader field of view and show more of the context information from the surrounding tissue. It has also been shown multiple times, both by our research group as well as other researchers as well, that including images from multiple scales improves the classification. As mentioned, the whole slide images consist of several tissue types which can't be used for grading. For tissue segmentation, these are the classes that we want to find. First, we have the urothelium, which is the tissue along the bladder wall and where the tumor will form. This is the main tissue type we want to extract. During biopsy, parts of the tissue gets both heating damage and also physical damage, and thus cannot be used. Also along the bladder wall, just below the urothelium tissue, there is muscle tissue and stroma tissue, and they are often present in the whole slide images. And as we saw a few slides ago, there will also very often be blood present in the images. And of course, we have background as well. If we have a closer look at the 3 tiles belonging to, for instance, the urothelium class, we see that the 3 tiles are extracted such as the center is the same in each tile. All the 3 tiles, they have the same size, but they are extracted at different magnification levels, and thus they will cover a broader field of view. And in my research, I refer to these 3 tiles as a triplet. Here we can see an overview of the proposed tissue segmentation system. First, in step 1, a background mask is found using a thresholding technique on the gray background. We see that each tile in the image is either classified as background or non-background here. But we do not know what tissue it is yet. Then, in step 2, all tiles specified as non-background is fed through our multi-scale tissue model, which will output a probability for each tissue type. If the probability is above the 60% threshold that we have defined, we will assign that tissue type to the tile. And then finally, in step 3, we assign a color to each tissue type and can create our tissue segmentation images. Let's have a closer look at the multiscale model from step 2 on the next slide. So this is the block diagram of the 3-scale model architecture. It is called 3-scale because it uses tiles extracted at 3 magnification scales as input. Each of the tiles are fed to individual VGG16 networks, which is acting as feature extractors. And then we are using the global average pooling layer to transform the 3-dimensional vector into a 1-dimensional vector. The 3 feature vectors are then concatenated and fed to the classification network. And finally, we have a softmax on the output layer. Here is the main result for the tissue segmentation method. In the paper, we did a lot of different experiments like multi-class and binary class. We tried with frozen and unfrozen base model, and as well as 1, 2, and 3 magnification levels as input to the model. I will not go into too much details about the experiments, but the overall best model for the multi-class model was the 3 model, which used tiles extracted from all 3 magnification levels. Here is an example whole slide image and then the corresponding tissue segmentation image. One of the things that pathologists are interested in, and they also must report in their findings, is the present or absent of muscle tissue in the slide. And if we remember how large these whole slide images are, it can be very time-consuming to search through it all, especially if what you are looking for is not there. With the help of these tissue segmentation images, we can easily spot the green region in the middle of the image, which represents the muscle tissue. The tissue segmentation images can also be used to guide pathologists to the diagnostic relevant tissue. Here we have another tissue segmentation example, and notice how quickly you could determine the absence of muscle tissue in the slide. As you see, these images can help pathologists become even more efficient in their work. There are also a few more examples of these segmentation results in the paper. Next, we have a few slides for multi-level tile extraction. So we needed a system which could automatically find and extract tiles in the whole slide images. In our method, tiles are extracted from each level, such as the center pixel is the same in all tiles, as we can see from the figure. We can see the center is the same through these tiles. A tile on one level is checked against a region of interest, and if it satisfies a certain criterion, it will be considered a valid tile. Then the corresponding tiles are found from the remaining levels. Let's start by looking at how we are finding the valid tiles. For grading of bladder cancer, the tissue border contains important information, and thus we needed a system which would include this in the tiles. We solved this by including a parameter called phi, which controls how much non-region of interest to allow in the valid tiles. In the example image here, we have a red tile, and to determine if this tile should be valid, it must satisfy the equation on the slide. The left-hand side of the expression, we have a double sum, which summarizes the pixels within the tiles area in the binary mask. So we are summarizing all of the pixels inside here, this binary mask. And this binary mask contains ones for the region of interest and then 0 for all the non-region of interest. The right-hand side of the expression is the total area of the tile multiplied with the parameter phi. So it means that a lower value of phi would allow for more non-region of interest in the valid tiles. We also have this R element that you see in the equation, and this is the ratio between the binary masks level and the tiles level. Now, if the binary mask and the tile is on the same level, this ratio simply becomes 1. However, it is rather convenient to include it, as it allows for the tile and the mask to be on different levels, which I will show you in a few slides. Once we have found a valid tile, we would like to find the corresponding tiles on the remaining levels. Tiles are usually referenced by the top left corner. However, when we are going between levels, it is convenient to use the center point of the tile. And we do this by adding half of the tile's length, LT, and then transform this position to the corresponding level by multiplying with the ratio between the two levels. So here we are adding half of the tile's length, and then we are multiplying with the ratio between the two levels we are transforming. After transformation, we need to return to the upper left corner, and we do this by subtracting half of the tile's length again. Another thing we wanted from our method was to be able to visualize tiles from all levels onto the same image. If we start to looking at the figure at the bottom, we have our pyramid and we have a tile on each level. We want to display all of these tiles onto the same level, in this case, level 2. And to do that, we need to transform all the tile to this level. And as we saw earlier, when we do this, the apparent size of each tiles also changes. And that's the reason why we're multiplying the tile length LT with the ratio between the two levels in the transformation. And we do this to get the correct output size. To transform the tiles, we use the same expression as before, but with some small changes so that the transformation instead goes to the highest level. So we have Kmax here. This transformation of tiles is illustrated in the figure. The left-hand side of the figure represents the input coordinate to the equation, and then the right-hand side represents the output. So let's look at a demonstration of the methods. Here we have a whole side image, and we have superimposed a purple mask for the urothelium tissue and also a green mask for the stroma tissue. As we can see here, I have set the phi value equal to 0.4. It's quite a low value, so there will be quite a lot of background in some of these tiles. And we can see that we are searching for valid tiles on level 25x. So we are using the largest of the 3 tiles to search for valid tiles. And in this case, we can see that we only find 29 tiles. Here we have the same image, but we are now using level 100x to search for valid tiles. Because the image is larger, the tiles appear smaller, and there are also room for more tiles. And in this case, we find over 600 tiles. And lastly, we can search for valid tiles on the highest magnification, 400x. And now we can see that we are finding over 9,000 tiles here. And for each tile in the image, we are, of course, also finding the corresponding tiles from level 25x and 100x, but they are not shown on the figure. Here is a side-by-side comparison of another whole side image. So the advantage of finding tiles on level 400x is a large data set. However, this data set will contain redundant information on the other levels. If we instead find the valid tiles on level 25x, we get a smaller data set, but each tile will be unique on all levels in the image pyramid. Notice also what I mentioned a few slides ago regarding the ratio R in the equation. In this slide, the binary mask is the same. The binary mask is on the same level for each image, but we change what level the valid tile is on. And this is the reason we needed to include a ratio in the equations. Lastly, some other usage scenarios for this method. In image A, we can see the method used to extract tiles. And if we use the X and Y coordinate and combine it with the predicted output from the model, we can use it to display the output. For instance, in image B, we have compared the prediction of the model with the ground truth, and then we are using the colors green and red to display correct and incorrect predictions. And in image C, we are using the probability score from the model, and we feed it through a color mapping function to create a heat map of the model's prediction. And we will see this again in the final model. And then finally, we have reached the last topic of this presentation, automatic grading of urothelium carcinoma slides into low and high grade. In the figure, we can see some example slides of both low and high grade tissue. Now, the different cancer types have different grading scales, but in general, if the cancer cells are similar to that of healthy non-cancerous cells, then the grade will often be low, and the cancer will have a lower likelihood of spreading. On the other hand, if the cells have a more abnormal appearance and are more disorganized, then the grade will often be higher. There are guidelines introduced by the World Health Organization, which specifies a set of features which are to be examined to determine the final grade of the tumor. The labels used in this work are according to the WHO 2004 guidelines. Through the Stavanger University Hospital, we have access to a large set of whole site images with corresponding gradings. However, we do not have any annotations to where in the image the low and high grade regions are located. Instead, each extracted tile will inherit the slide level grade as its label. However, this is not ideal, as high-grade slides may contain regions of low-grade tissue, and consequently, all of the extracted data sets are thus regarded as weakly labeled due to the inaccurate labels used. This slide shows the dataset used in the paper. We can see that for training, validation, and test set, we have a total of 220, 30, and 50 whole slide images. For the validation and test set, the tile extraction method is used to find tiles, and all tiles are used in the dataset. For the training dataset, however, only n randomly selected tiles have been extracted, and we are in the paper, we have set n to 250, 500, 1,000, 3,000, and 5,000. And the image to the right shows how the density of tiles varies with the different values of n. Here is the full diagnostic pipeline. It is called TRI-GRADE, and it consists of both the TRI-tissue model and as well as the WHO 2004 grading model. As we have seen earlier in the presentation, in step 1, a foreground mask is found from the slide and used as a reference to feed all the foreground tissue through the tissue segmentation model in step 2. This creates the tissue segmentation map, which can be of great help to the pathologist. Next, in step 3, a binary mask is created for the diagnostic relevant urothelium tissue. If we compare the binary mask in step 1 with the binary mask in step 3, we can clearly see how we have filtered out all of the unwanted tissue. In step 4, the binary urothelium mask is now used as a reference, and then triplets of urothelium tissue is extracted, and in step 5, they are fed through the grading model. The proposed pipeline will create a grading heat map and also an aggregated slide level grading. Here is the main results for the 3-grade method. Each of the trained model was evaluated on the 50 slides in the test set, and then the predicted grade was compared with the pathologist grading on the slide. The best model was the one trained on the largest training dataset. It correctly graded 45 out of the 50 slides in the test set, achieving a score of 90%. The results were also compared to the work of Janssen. The results are not directly comparable as they are evaluated on different datasets. However, both work are carried out on a similarly sized dataset. They are using the same grading classification system, and they are split into training, validation, and test set with similar size. And as we can see, our proposed model outperformed the work of Janssen with our result of 90% accuracy. To further evaluate our model, 14 of the 50 slides in the test set was manually annotated by a pathologist. A few large regions of either low grade or high grade was annotated on the images. The same area was then classified by our model and compared to the ground truth. Here we have one of the 14 annotated images. The black image to the left is annotated by the pathologist, and the model's prediction is shown in the gray image to the right. And we can see that the model correctly identifies the region as high grade. Here we have another image, and this time the pathologist has annotated low-grade regions. And once again, we can see that the model correctly classifies the regions as such. Here is the full list of all 14 slides annotated by the pathologist. And to the right is a table showing the result for each slide. As we can see, the model does an excellent job at correctly predicting the regions. However, if we look closely on image N down here, we see that pathologist has annotated a high-grade region and the model has predicted it as a low-grade. We asked the pathologist to re-evaluate this region, and he stated that the region consisted of a mix of both low and high-grade features, and thus he classified the region as high-grade. But nevertheless, as mentioned, the model did an excellent job at the remaining slides. I also want to mention that the code for all work I have presented today is available at GitHub. And with that, I would like to thank you all very much for your attention.